Alright, today we're going to talk about characteristics of polynomial functions. Going to talk about some new stuff today that really we haven't even touched on. So a lot of these ideas are going to be new. I don't think they're hard, but they are definitely new. And a few of those definitions, they're up at the top. So your absolute maximum, that is going to be exactly what it sounds like. It is going to be the highest point on the graph but if you're ever asked to identify it, it cannot be infinity. Okay, it will never be infinity. So you might be asked, does this graph have an absolute max or an absolute min? Well, if it's just a parabola, that graph right there, that would have an absolute max. This parabola would not have an absolute max because those will go up to infinity, but that one would have an absolute minimum. And that absolute minimum is the lowest point on the graph. But this cannot be negative infinity. Okay? So I don't think those are very hard concepts. We've talked about whether a vertex is a maximum or is a minimum. Some of the graphs we may see in this unit, it's not a vertex. All right, you may have something like this, where this is the absolute minimum, and this graph would not have an absolute maximum because your end behavior goes up to infinity. Really, one of the new things is going to be what is called an extrema, which if you will change that S to an X, there's a typo on there. Extrema. This is when the graph changes directions. To put it in simple terms, a way that you can think of it is anytime the graph curves. Okay, so if I was to graph something, this would be considered an extrema, that would be an extrema, and that would be an extrema. So this would have three extrema. That specific graph would have three extrema on it. Alright, so this first page, we're going to come down here, we're going to look at the number of extrema on these different graphs. And you need to kind of come up or draw a connection between the degree of the polynomial, which remember degree, that's the largest exponent, the degree of the polynomial, and the number of extrema that you could possibly have. Alright, so looking at these graphs right here, hopefully this is pretty self-explanatory. You're just counting the number of times it changes directions. So on this first one, this is a fourth degree polynomial. Both of these are. That first graph, it comes down and then it curves back up. So it only changes directions one time, so it would have one extrema. The next one goes down, comes back up, goes down, comes back up. So this one would have 1, 2, 3 extrema. Remember, this is all on a fourth degree polynomial. Going to a fifth degree polynomial. Whenever you have these odd functions that look like this, it's a little this part right here can sometimes confuse people, but it never actually starts to decrease if you're looking at it going from left to right. Okay, it just kind of flattens out, but it's always, even if it's slightly, it's always increasing. So this one never changes direction, so it would have 0 extrema. Your next graph, I've got an extrema right there. I also have an extrema right there. So this one would have 2. My next graph, I've got 1, 2, 3, 4 extrema. And again, remember, these are all fifth degree polynomials. On your sixth degree polynomial, a lot like the fourth degree, it goes down, it comes back up. that is only giving you one extrema. On my next one, I've got 1, 2, 3 extrema. On the last one at the bottom right, this one's a little hard to see, especially in this area right here. But you would have 1, 2, 3, 4, 5 extrema. Alright, so make sure you're kind of noticing the possible outcomes that you can have for each kind of degree. Okay, because we're on the first question on the next page, it's going to ask us what we notice about that. So if you will turn to that page, let's go ahead and write that in. We got 3 different things we need to write in that little space. Probably should have given you more space than what you have, so make sure you're writing small. If it is an odd degree polynomial, then they have an even number of degrees. Sorry, even number of extrema. Okay, because if you look back, those odd degrees, we had that it was just a 5th degree polynomial, but it had 4, 2, and 0. All right, and those are the only number of extrema a 5th degree can have. If it is an even, degree polynomial, it will always have an odd number of extrema. Alright, the last thing that you need to know is the max number of extrema that a polynomial can have is 1 less than the degree. So if it's a 7th degree polynomial, the maximum number of extrema that a 7th degree polynomial can have is 6 extrema. Is 1 less than the degree. Okay, so again, really looking on this lesson, really looking at the degree. What does the degree tell us? Right now we're just looking at the extrema. So on the next question, these 4, a 9th degree polynomial, 1 less than 9 is 8. That's the max number that it can have. And because 9 is an odd number, it can have any even number of extremas. 8, 6, 4, 2, 0. Alright, so if you just take the degree and you subtract 1, that's the max. And then from that max, you just count down by 2's. Alright, so a 9th degree can have 8, 6, 4, 2, or 0. It cannot have 10 extrema. Okay, you won't count up. So an 18th degree polynomial, the most it can have is 17. And then 15. And then 13. Now, for the sake of time and sanity, we'll get rid of that. Just put point, dot, 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 so that pattern continues, just counting down by 1. Alright, and it can have 3, or it can have just 1 extrema. Alright, so an nth degree polynomial, alright, again, the maximum, you're always just going to subtract 1. Alright, and then from that, this ends up being, the next option would be subtracting 3 from that polynomial. But just from that maximum, again, you're just counting down by 2, so that's all it is. The big thing you need to know here, though, that an odd degree polynomial, it can possibly have 0 extrema. Alright, for an even degree, nth degree, this should say even. Okay, same rule applies in -1, in -3, and so on. This one can't have 0 extrema. The least number of extrema that an even degree can have is 1. You'll never have 0 extrema on an even degree. Okay? So the next part of the notes, just coming down, there's a few statements just to kind of, make sure that you know just a few rules on the extrema. This talks about relative extrema. Just any time it curves, and at the very beginning of the notes when we defined what an extrema was, probably should have put a relative extrema. Alright? Anytime it has an absolute max, an absolute extrema. Sorry, I'm losing where I'm at. An absolute extrema, that's going to be your absolute max or absolute min. Okay, and we'll go through a few examples that we'll talk about that here in a minute. So on this, it says an odd degree function will blank have an absolute extrema. Okay, an odd function will never have an absolute extrema because it will always either start down, it might do all that stuff, but it's always going to go up. So remember, on those definitions, we said our absolute max and absolute min can't be negative infinity or positive infinity. So an odd degree is just never going to have an absolute extrema. An even degree polynomial will always have a relative extrema. Alright, so let's just take the basic example. And even though this is an absolute extrema because it is the minimum, an absolute extrema is always a relative extrema. A relative extrema is not always an absolute extrema. Okay? And I'll give you a better example of that right now. Okay, so we may have this right here. Relative extrema, relative extrema, relative extrema, relative extrema. This is the absolute extrema, but it is also considered a relative extrema. Okay, so this is the one that is both a relative and an absolute because it is the lowest point. So it would be an absolute minimum. An even degree function will have 3 or more extrema. This would be sometimes. Okay, an even degree, it can have 1 extrema if it's just that x squared I just had up there a minute ago. An even degree function will always have an absolute extrema. Whether it's an absolute max or an absolute minimum, it will always have an absolute extrema. An odd degree function, just going to put S on there, will sometimes have a relative extrema. If I just take the parent cubic function, the one we've been talking about here lately, that does not have a relative extrema. That has 2 relative extremas. Okay, so it can have one, but it can also not have a relative extrema. An odd degree function will never have 1 relative extrema. Okay, because remember, an odd degree function can only have an even number of extremas. An even degree function can only have an odd number of extremas. Going here to this table right here, we'll answer these questions. Kind of getting into the, zoom in a little bit for us. Okay. So it says, state the similarities and differences you notice between the power functions and polynomial functions. Alright. If it is an even degree that is positive, there's the power, there's the polynomial. Both of those are up, up. Okay. If it's negative, it's down, down. Now going to my odd degrees that are positive, there's the power function, it's down, up. Polynomial is down, up. If it's negative, power is up, down. Polynomial is up, down. So what that tells me is that they have the same, whether it is a power or a polynomial, they have the same end behavior. Also, a power function has either one, that would be my even degree, or odd, sorry, 1 or 0 extrema. Okay, my even degree power functions, they have one extrema. My odd degree power functions, remember those never change direction right there around the origin. Those are the ones that have 0 extrema. So going to question B, it says, what conclusion can you make about the end behavior of all even degree polynomial functions? If the a is positive, then as x approaches negative infinity, y approaches infinity. If x approaches, as x approaches infinity, y also approaches infinity. Versus if the a is negative. If the a is negative, then as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches negative infinity. Alright, remember that is referring to an even degree, which is these top two. Those are both up, up. If a is positive, they are down, down if my a is negative. Question C says, what conclusions can we make about the odd degree? So if a is positive, as x approaches negative infinity, y also approaches negative infinity. As x approaches positive infinity, y also approaches positive infinity. Versus if the a is negative, so if you haven't noticed, that's really what makes the difference, whether the a is negative or positive. As x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y approaches negative infinity. Okay, so make sure you have all that written down. This is also, this is the table we had in, I think it was 4.1, 4.2, the first lesson in this unit. Just writing all those end behaviors, depending on whether it's even or odd, and then also if the a is negative or positive. Alright, so let's go to this next page. We're going to look at two different graphs, and we're just going to answer some questions about it that we've been talking about. Just looking at those different characteristics and finding those characteristics on the graph. So if my end behavior is going in the same direction, that's kind of the first thing you need to notice. Whether they're both going up, both going down, I don't care, versus whether they end up going in opposite directions. If they're going in the same direction, that tells me that this is an even degree. And then if both those are going down, both my y end behaviors are going to negative infinity, that tells me that I have a negative a value. That should be really one of the first things you notice right there. Is it odd or even? And then is it positive or negative? I think it's easy to determine the positive and negative on an even degree, because if both my end behaviors are going up, then it's even. Sorry, if it's positive. If they're both going down, then it's negative. The next question asks, can this function be a sixth degree polynomial function? I can determine this by a couple different ways. And we haven't emphasized this a lot. I mentioned it a little bit in the first lesson. If you have a sixth degree polynomial, and we're going to fill out a nice neat chart on the back of this, or after this page, the maximum number of x-intercepts that a sixth degree polynomial can have is 6 x-intercepts. That's what the degree is telling you, is the number of x-intercepts that this could possibly have. Alright, so I can look at this two different ways, because I look at my x-intercepts. I've got 1, 2, 3, 4. As long as it's 6 or less, it could be a sixth degree polynomial. So I would write yes. One explanation can be that there is less than 6 x-intercepts. The other way I can tell is the number of extrema. This one has 1, 2, 3, 4, 5. And as we've already talked about, the maximum number of extrema is always 1 less than the degree. Well, if the degree is 6, the maximum number that it could have is 5. And so I can look at it and say that my explanation can be that it has 5 extrema. D says to state the domain and range of the function. Anytime you're doing an even degree, I want you to think of a parabola, the rules of a parabola. Well, my domain for a parabola is always negative infinity to positive infinity. My range, it's going down to negative infinity, so that needs to be my first part of my range. And then it is going up to this absolute extrema, let's just say it's 2.25. And it is equal to that. Question D says, determine the number of relative extrema in this graph. We already identified that. That was 5. We talked about that up in question C. F says to determine the number of absolute extrema in this graph. It will have 1. Alright? It's a weird looking 1. There you go. You can only have either 1 or 0 absolute extrema. If it's even degree polynomial, you're always going to have 1. If it's a non-degree polynomial, you're always going to have 0. Absolute extrema. The relative extrema, that's determined by the degree. G says state the intervals where the graph is decreasing. So all you would do there is you would look at the graph and you're writing essentially the parts of the graph that's decreasing. You're writing the domain for those parts. So that first one, let's say that is negative 2.5 to negative 1.5. The next part that is decreasing is up here. Let's say that's 1.5 to 2. And the last one, that's at 3, and it's going to positive infinity. I know it's going down, but remember we're looking at the x values. You don't want to see that as going down. It's going to continue to slightly go to the right, which is positive infinity. I need a parentheses on that because it's infinity. I can't be equal to that. Okay, so let's go to the next question, answering the same kind of ideas. So my arrows are going in opposite directions of each other. So that right there should tell me that it is an odd degree. If it ends up going up on the right, then it is positive. If it had ended up going down on the right, it would be negative. So you really need to look, does it end up being an increasing graph, or does it end up being a decreasing graph? This one is increasing, so it would be positive. Can this function be a cubic function? Why or why not? So I've got 1, 2, 3, 4. So according to what I told you on the last problem, the maximum number of x-intercepts a cubic function can have would be 3. This one has 4. One of my explanations I can have would be too many x-intercepts. My other one would be too many extrema. Because if it's cubic, the maximum number of extrema that it could have would be 2. Well, this one has 1, 2, 3, 4 extrema. State the domain and range of this function. Anytime it is an odd degree, your domain and range is always negative to positive infinity. unless it is a word problem that restricts your data. E says determine the number of relative extrema on this graph. 1, 2, 3, 4. And because it is an odd degree polynomial, it will not have an absolute maximum, because it's going to end up going from negative infinity to positive infinity. G says to state the intervals in which it is decreasing. So same idea as the last one. This first one, let's say that it's going from negative 2.5 to negative 1. My next part that is increasing, let's say positive 0.5 down to 2.25. So those are the intervals in which that graph is decreasing. All right, going to the last page, and you might need to turn your packet around there to fill this one out. Let me see if I can flip this page so that you can see it better on the screen. Alright, so I got it flipped over so that you can kind of see it better up on the screen. So looking at this, on this we're going to look at the number of x-intercepts that these different degrees can have. Now on the left there, it doesn't say even degree, odd degree, first degree, fourth degree, whatever. It's giving you the name of the actual function. So make sure you know what that is. This is a first degree. If a linear graph that has 0 x-intercepts would just be a horizontal graph. A linear that has 1 would be any of them that would cross the x-axis. Okay? It will never have any of these. If you have a quadratic, which is x squared, it is possible for you to have a quadratic graph that does not have an x-intercept. It is possible for you to have a quadratic graph that has 1 x-intercept. It is possible for a quadratic to have 2. 2 is the maximum number of x-intercepts it could have. If you have cubic, which is x cubed, a cubic will at least have 1 x-intercept always, so that might just be that parent cubic function which we've graphed before. An example of a cubic function that might have 2 is one that would go through the x-intercept, come down, it looks like it kind of bounces off and then goes up. What a cubic graph might look like that has 3, instead of bouncing, it crosses through and then goes back up. A quartic, so this is x to the 4th. This is possible that it would not cross the x-axis. This looks like a parabola that is just a little bit wider. You saw these, I believe it was 4.2, 4.1, 4.2 notes. Okay. It is possible for it to come and then just barely touch it. It is also possible for it to just go through. So everything right now on quartic is the exact same as quadratic pretty much. It's just they look a little bit wider. So this is whenever it gets a little bit different on that. Because if it's x to the 4th, the maximum number it can have is 4, and then it can have 3 x-intercepts, 2 x-intercepts, 1 x-intercept, and none. So one that would be 3, it would cross through, it would come back, and it would bounce off. Okay, that has 3 of them. And then one that would be 4 would just kind of look like a W. Next, going to the quintic, so this would be x to the 5th. everything on this up to 3 x-intercepts is all going to look like the cubic. But I need to be able to make a graph that has 4 x-intercepts and also 5 x-intercepts. So I can go 1, 2, 3. I've got to make a fourth one, but I know I've got to finish going up. So it bounces and goes up. And then on a fifth, starts down, goes up, and on that last one, instead of bouncing, it goes through the x-intercept and then goes back up. Alright, so this is just a little table talking about the x-intercepts, the possible number of x-intercepts given the degree. Alright, so you need to make sure that you're aware of that a fifth degree can have up to 5 x-intercepts. It could also have 1. Alright, so these are the notes. You should be getting your homework once this video has stopped, and I hope you have a good weekend.